we will cover the atomic and molecular application on X-ray spectroscopy. X-ray diffraction is only briefly discussed, and surface analysis and microscopy is also briefly discussed in advance on its own lecture. So X-ray absorption processes, we have the Auger, electron emission, and photoelectron emission. So excitation of X-rays, we have X-ray fluorescence, then we have X-ray emission, then X-ray detection and spectrometer design. We look at energy-dispersive spectrometers and wavelength-dispersive spectrometers. So methods and applications, topics mentioned here but discussed in detail during the surface analysis and microscopy lecture. We look at just briefly scanning electron microscopy, Auger electron spectroscopy, and X-ray photoelectron spectroscopy. Then if you look at electromagnetic spectrum, we are going to realize that the X-ray we are talking about is this. Where we have the X-rays, and we have also partly the gamma rays. X-ray emission, the one that we are going to look at, are commonly produced by bombarding a target with electrons. The target emits a spectrum with two components: characteristics radiation and continuous radiation. This continuous radiation is also known as white radiation. The Duen-Hunt limit explains the cutoff of the continuous radiation. So you can be able to see this equation so that diagrams already, the N, L, S and J, the spin, and then now you will be able to understand. So that is K alpha tau. If it is coming from 3p and then that spin, then it is called the K beta 1, and the same we have the K beta 3. So some of the X-ray generation characteristic radiation you can be able to see. So in future we are thinking of the goals are short pulse sources, brilliant sources, coherent source, and small beam sizes. One way of getting there is capillary optics, which can achieve a higher spectral efficiency and small spot size for a given X-ray beam. So design generally is we have a radiation source, then goes to the sample, then we have wavelength selector, then we have detector. So that is when we talk of energy wavelength dispersive spectrometers. Then if we talk of energy dispersive spectrometers, detects the portion of a spectrum directly through its energy. So we don't have wavelength selector anymore. Very simple. So most substances have refractive indices of unity at X-ray frequencies. The reason X radiation is so high frequency that there is no time for the electronic polarization needed to cause a refractive index. Therefore, mirrors and lenses for X-ray cannot be made. It means that we cannot have a refraction, and other ways to control X-ray must be found. So X-ray can be diffracted by crystals. Just like we do in other optical spectroscopy, where we use Ekele gratings. The wavelength of X-ray is so short that only molecular diffraction gratings can be used. So energy-dispersive analyzers. Energy-dispersive analyzers are heavily used in X-ray fluorescence, especially portable or small footprint. Electron microscope, like in the scanning electron microscope. The spectrometer is just silicon lithium detector. So silicon lithium detectors are made of silicon and doped with lithium using cool liquid nitrogen or refrigeration system, usually called lithium drifted silicon and drifted germanium. The detector is polarized with a high voltage. When X-ray photons hit the detector, electron-hole pairs are created that drift through the potential, creating a pulse whose magnitude is directly proportional to the X-ray energy. If an X-ray photon is absorbed by an atom and it has enough energy, it can eject an electron, leaving a vacancy. A higher energy electron will drop down to replace it, emitting a secondary X-ray. The energy of the secondary X-ray is the difference of the binding energy of the two shells. So X-ray fluorescence is a similar process to the photoelectric effect, where an X-ray is absorbed and transfer all of its energy to an electron. Both energy-dispersive and wavelength-dispersive spectrophotometers are widely used for X-ray fluorescence. So we can be able to see here photoelectron, an incident X-ray knocks an electron, leaving a vacancy here. In this X-ray fluorescence, a higher energy electron goes to replace or to fill the vacancy left, and then X-rays also emitted, and in other instances this X-ray can knock another electron, what we call the Auger electron. So X-ray fluorescence yield is actually influenced by the degree of Auger electron formation. Auger electron predominate at lower Z. So when we hear the word lower Z, is when the atomic number is low. You can see atomic number here, which is always denoted as Z. So X-ray fluorescence can be produced by X-rays, alpha particles, photons, electron beams, like in scanning electron microscopy. So you can be able to see the effect of Auger. So you can be able to see the same situation that we've been talking about over and over. Now these are some of the terms that are used so much in electron microscopy. X-ray emission is just one of a multitude of processes that can occur when electron hit a target. So you can be able to see there. Then in a scanning electron microscopy or transmission electron microscopy, the following are possible: X-ray emission spectroscopy, spectrometry with mapping, formation of images from backscattered electrons, diffractometric analysis. You can be able to see, just like electron-induced X-ray emission, only more efficient, less damaging to the sample but more sensitive, less charging than electrons, less lateral deflection. Protons are not multiply scattered like electrons. So you can be able to see you have an electron particle beam, then you can be able to see characteristic X-ray when this one is knocked, and then one electron comes and fail the lower energy hole, then an X-ray is emitted. two regions of X-ray absorption fine structure spectrum. So we have the extended X-ray absorption fine structure, which is sensitive to distances, coordination number, and identity of surrounding atoms. Then we have X-ray absorption near edge spectroscopy, sensitive to oxidation state and coordination. For example, tetrahedral versus octahedral coordination over an atom. So you can be able to see an example of X-ray absorption fine structure for iron oxide. On top, the measured X-ray absorption fine structure spectrum is shown with the X-ray absorption near edge spectroscopy and X-ray absorption extended X-ray absorption fine structure region identified. So scanning Auger X-ray, so you look at scanning Auger. All are surface analysis methods and will be discussed during the microscopy and surface analysis lecture. So that is all. We welcome you to microscopy lecture so that we may expound more on this class. Thank you.